Good afternoon, everybody, and welcome to the weekly Firaxis live stream. My name is Pete Murray. I'm joined today by a very special and distinguished guest, Dr. Joel Green of the Space Telescope Science Institute here in Baltimore. We are here today to do a very cool show on the science of beyond Earth and a little bit of the science of rising tide. We're going to play some beyond Earth, not rising tide. We'll get to rising tide soon. We're going to talk about some cool intersections of astronomy work that's being done today and the game itself. And I'm going to give you an opportunity to meet Joel. And if you're in the Baltimore area, Joel, and you're free this weekend.
On Saturday, we're doing our first, the inaugural Astronomy on Tap Baltimore version at the Auto Bar at 7 p.m. You're going to hear 3 talks from distinguished astronomers and myself. Most notably, the Mars One finalist, Sonia Van Meter, will be speaking about her experiences with that program. And then Space Dance, a big dance to astronomy images and amazing space stuff.
So if you like beer and science and you live in Baltimore, you should definitely check it out this Saturday. It's a holiday weekend. You don't need to go into work the next morning. That's very cool. Also, Joel is the person who kicked off our Systematic Destiny short story series that's been up on civilization.com. So thank you very much.
That was a lot of fun to write.
Yeah, we had a lot of fun. So the last piece of that, part 6, should be going up today. And then after that, we're going to put them all together and you'll be able to read them all as one story. So it's sort of set around the time of the seeding, all the way through to on Earth to after the colonists have left and them coming back. So it should be very cool. And I see right now, part 6 has gone up. So if you can open another web browser tab, go to civilization.com, check out Systematic Destiny Part 6. Very cool. So
yeah, that was great.
We had a lot of fun with that.
Some of the challenges of the people in the Systematic Destiny blog are real challenges for astronomers. I mean, it's one of the things we do is we look for planets, and you imagine being in this setting of this dying Earth looking for another world, and some of the issues that they're dealing with are real problems. Yeah, and what's really cool now is, especially with all of the work that's been done on exoplanets in the last 3 to 5 years, and cataloging them and finding them. It's been an exponential growth in our knowledge of other worlds.
It's been pretty crazy. Now, you're lucky at the Space Telescope Science Institute. You guys work with the Hubble Space Telescope. You guys are having your 20th anniversary. There's already a cool tie-in.
25th, actually.
25th, I apologize. The cool tie-in between Hubble and Civ. It's a wonder in civilization, and I think it's what's it like to be able to work on kind of the crown jewel of the American space program?
Well, I'm a recent transfer to Maryland, so yeah. This has been an amazing experience for me. So I've been doing tons of research up to this point, and I used to live in Austin, Texas.
Yeah.
I worked at the University of Texas at Austin, and then I started here, and so I'm the sort of project scientist in the Office of Public Outreach at Space Telescope, and that's a really amazing place to be because that is basically the biggest outreach organization, for any of the astrophysics missions, and Hubble is the flagship mission of NASA in terms of science and astrophysics, and it's been going for 25 years. It launched in 1990, which is I think the same year that, or maybe the year before Civ won.
Yeah, so they've kind of had this parallel life we were talking about earlier. That they've been Civilization and the Hubble have been around for roughly the same amount of time.
I think I got inspired by both right around the same time, actually.
That's
give away my age. I was about 12 then, and I started out playing simulation games, and I was, and reading science fiction, and so I think I got pulled into my interest in science and astrophysics actually was spawned a lot by games like, the Endgame of Civilization or Master of Orion and all those others. And so it's been really, and Alpha Centauri. And it's been an amazing ride. And so it's funny that the two have sort of had regular releases or updates or servicing missions from 1990 until now. And both are vastly different technologies than they were in 1990.
Yeah, it's pretty good. And you said this at lunch today that I thought was interesting. There have been 5 servicing missions for the Hubble, and there have been 5 iterations of Civ as well too. So
that's right.
We're clearly right there with each other. That's pretty awesome. So Civilization Beyond Earth is a game about settling an exoplanet, and we do some things in the game that are sort of inspired by actual science. But I wanted to talk. Or gamey, and I wanted to kind of play a little bit today, and we could talk about how actual science intersects with some of the things that are in the game. So let's jump into our game as we're going right now. So we've just fired up this game because we're going to launch something in a few turns. We're playing here one of the big hooks for Rising Tide and is going to be the water gameplay. And here we have this lake and this crater here. And earlier you said that it didn't take anything very big to make a big crater.
Yeah, it's a really nice looking crater you guys have in there, actually.
Thanks.
You'd expect maybe you'd see a little central peak where from the reaction of the tiny meteorite that crashed into the planet to make that thing.
Right. But standing water, it turns out we're not entirely sure how it got here on Earth just by itself.
The delivery of water to the Earth is definitely a hot topic in astrophysics, and there's not just one answer. There are many thoughts on how that goes, and it all actually, what it relates to is the formation of solar systems like ours and others. Mm-hmm. And so one of my areas of research is to study how do solar systems form and sort of what are the bumps along the way that you would experience and what are the different paths that could take. So it's sort of both from a sort of theoretical point of view and then from an observational, because we can actually watch the formation of other planets and stars. They're sort of linked. Stars and planets form together, and because this happens throughout our galaxy, and I can kind of explain some of the details of that. But.
Sure. So Earth-like planets like this lush biome we're playing on, we know now from surveying exoplanets that the idea of an Earth-like planet seems a lot less strange than it did, even 10 years ago. That this is something that clearly happens out there in the galaxy.
I mean, we had thought that there were other planets.
Right.
Right, but no one had ever detected directly another planet around another star until 1995. That was the very first detection of an extrasolar planet called 51 Peg-P.
Okay.
And the first image of another planet was taken in 2008. Well, two of them, one by the Hubble Space Telescope and one by the Keck Observatory.
That's pretty amazing.
Yeah. So 2008, that's from direct imaging of planets, any planets.
Wow. So what do you see when you directly image a planet? I mean, you don't clearly get like the pale blue dot level view of something. I mean, is it just, and how do you determine, how do you even figure out that's a planet versus something else?
Planets that are imaged are not very pretty. They kind of look like little blobs next to other really bright blobs. Mm-hmm. One of the challenges, if you want to take a picture of an actual planet from around a distant star, the problem is that the planet is pretty close to the star, and the star is 1 billion or 1 trillion times brighter than the planet.
Right.
And so it's very difficult to separate that one photon of light from the planet from the 10 billion from the star that's right next to it blasting it out.
Right.
So you need special equipment to do that. And so it took, so you can do that in a couple of different ways, but the idea essentially boils down to taking your thumb and blocking out the starlight and trying to squint and see that little dim thing next to it. Now, it's done a little bit more technically than that, but you might use something called a coronagraph or maybe an external star shade or something like that.
But it is essentially the analog, the high-tech analog of taking your hand and kind of blocking the sun so that you can see down the road or something like that.
Yeah, it's a shade.
Yeah. Oh, wow.
And so when you can accomplish that with sufficient precision, then you can detect these planets. And that's why it took so long, and that's why only the brightest planets that are relatively far from their star are picked up by this method.
So these are planets like these super Jupiters that people talk about.
Yep.
All right.
So,
sorry, real quick, I'm going to jump into the game real quick. We've got the JGR1 Space Telescope, which aside from looking awfully like your initials, stands for, we decided, the Joint Great Resolution Network, that it was a series of tiny, relatively speaking...
it's a colonial telescope.
A colonial telescope. So...
or an array.
An array. So we talked a little bit about other space telescopes that your group is working on and that kind of are planned for the near future. And there's some pretty cool ones coming up.
No village was ever ruined by change.
Hang on,
what
real
is he
quick.
saying?
He wants to give me a favor.
For money.
Actually, he wants...
Oh, and open borders.
Open borders and energy per turn. Go away, Barre. Not.
That didn't seem like a very
That's a terrible offer. Open borders is kind of Barre is really strong. I don't want him down here messing around.
I noticed we're a little unhealthy as well.
We kind of just let this game play up a little bit because we want to launch this ridiculously overpowered satellite in just a moment.
I'm very excited to see it.
It's going to be absurd. I'm not going to lie. So we'll go ahead and we will found our new outpost. Unfortunately, I have this trade convoy that's waiting to resupply it up here. We'll establish trade route. We'll grow our outpost. And we're just 2 turns away from pointing JGR1. So what are some of the other space telescopes that you guys have in your hip pocket ready to go?
So the Space Telescope Science Institute, where I work, is sort of a freestanding institute of 110 research staff astronomers,
Right.
and many other engineers, software engineers, and developers, and things like that, and programmers and writers, who operate the science mission of the Hubble Space Telescope. So that means that we take in the data, we take pictures, and we make all the beautiful images that you're familiar with Hubble, and we reduce the data. We produce archives so that anyone in the public can access them. There's 1,000 scientific papers a year that use Hubble data. Scientific
Really?
papers, half of which use data from the archive rather than new data being taken by Hubble now.
So
So it's all stored for eternity.
So you don't even need to get out there and see it live. You don't.
That's right.
You can make significant contributions to astronomy as a science based on things that Hubble has.
You don't have to be the originator of the observation to come up with a neat project.
That's amazing.
Because there's so much data to mine.
What kind of things have you guys? What's an example of this archive data been used for?
Well, so there's a lot of observations that are. So what sometimes will happen is you'll have a phenomenon will change or burst. Say a supernova will go off.
Right.
And so you'll have a previous measurement, just by chance, of a galaxy or a star system that was in an earlier state, and then you take this new observation, you combine the two,
Yeah.
and you can say, oh, look what changed. We got a new.
There's a
we
new
know
nova
that
there.
that's different, or that star just changed brightness, or that there's a planet that's orbiting and it's occulting part of the light from this star, or whatever it is. Or, we can sense the difference between the atmosphere of the star and the atmosphere of the planet by the time component. So there's a lot of time variability, and then there are just projects where there's more than one. There's more than one reason you would take the data. So say, for example, you have a map of a galaxy, you're
Right.
looking for something in particular, but then afterwards someone said, hey, I'm going to look for all of those different kinds of galaxies and see what's in common between them. I'll pick through other people's data and say, can we figure this out?
Okay. Chat would like to know, is the Webb Space Telescope back on track?
So the Webb Space Telescope is definitely on track. Yeah, so the Webb telescope is the Hubble successor.
Right.
Right, so this is a much bigger telescope, and it's optimized for the infrared, and my institute, the Space Telescope Science Institute, is actually going to be running both the mission and the science operations of Webb. So the computers that are actually driving it will be there as well in Baltimore, and
as
all
well
the
as all
same
of the
archival functions and everything like
Awesome.
that. And so Webb is slated to launch in October of 2018, and it should not be slipping from that. We're actually a little bit ahead of schedule in most ways on the hardware especially. So right now the mirrors are being assembled. It's made up of 18 segmented mirrors. If you've ever played Settlers of Catan,
Or Civ 5 with
Civ 5,
hexes.
hexagonal.
Yeah, hexes,
it's 18 hexagonally arranged mirrors,
yeah.
and with a central stop where all the instruments are.
I'm gonna turn this on here. So, for example, the central stop would be that,
yeah.
and then all
It
of the
would be
mirrors
two
would
out.
be 2 rings out.
Yeah.
So, you want to see something really ridiculous? I'm gonna show you. We modded in this JGR1 space telescope. I'm gonna pause the actual science talk to show you.
Oh,
how
we've got to
ridiculous.
see this.
Yeah. So this space telescope produces +1 science and +1 culture for all the tiles beneath it, because we're not so much concerned about gameplay and
It's all balance.
or fairness. Yeah, we just wanted to make something fun. So not only does this generate tremendous amounts of science for the culture that produces it, but inspires artists and philosophers and elementary school kids, pets. Everybody loves this space telescope.
It's Mega Hubble.
We're going to launch this Mega Hubble. So Webb is
I like the design.
it's pretty cool. So this is a reuse of one of the game assets, but yeah, this is kind of ridiculous. So now if we turn on the tile yields, we can get out of the orbital layer. You can see we are adding a simply ridiculous amount of science on these tiles below that. And I'll toggle my yield on.
Yeah, how much did we jump up our cities?
Oh, a little
yeah.
bit.
That looks
a
good.
A little bit, yeah, that's going to go up. Plus,
I think we're winning now.
I think all about the beakers.
Unless the computer figures out that they should build them.
Actually, if we pull up the Fire Tuner, which is the tool that lets you kind of crack at the game, you will see that the AI is madly building these things too, because they're like, this is great. It's like catnip for the AI. So we'll turn that off. All right, let's jump back to the studio real quick, and we'll just we'll take a break from the game for a second. So you were telling me about another telescope that's got kind of a fun story to it. And so the Hubble is a single mirror telescope, correct?
Right. one 2.4 meter diameter mirror.
Okay. Is there another mirror like that out there in the wild?
It turns out there is a very similar mirror out there, and it came from a somewhat interesting source. So every 10 years, astronomers get together and decide what to recommend to NASA. What is the next big project that we should be taking on?
Right.
And so Hubble was the first one that came out of one of those, and then the Spitzer Space Observatory, which is still up, and the Chandra Space Observatory was one, and then Webb, the James Webb, was in 2000.
Yep.
Now the 2010 one was so when astronomers were deciding in 2008 and 9 what they were going to put in the report, the National Reconnaissance Office, which is an arm of the military, sort of happened to mention that they had this extra Hubble mirror, Hubble class mirror, so an extra 2.4 meter mirror, just kind of sitting around.
I wonder what they were going to use that for.
So one of the interesting questions is, that, it turns out it depends which way you point it,
Yeah.
whether it's, which department of the government that it's in. So we thought, gee, great, so we've got a mirror, so we should build a telescope to go with this mirror and an instrument set to go with this mirror. And so what kind of won the day with that survey was this, it's called the W-FIRST, or Wide Field Infrared Space Telescope, with this extremely large aperture. And so it's going to be used to make a new telescope that will follow on in around 2024. And it will be a bit like Hubble in terms of its coverage of frequency space.
Right.
But mostly visible, a little bit of ultraviolet and infrared. I think it has ultraviolet. Anyway, it certainly has infrared. But its field of view will be 100 times greater than Hubble. So 100 pointings of Hubble would be one pointing with this thing.
So this is a little bit like taking the telephoto lens off your camera and putting
Yes.
the fisheye lens on instead.
Very wide angle.
Okay.
But without hopefully we can correct the distortion so you don't get the fisheye look. So Hubble would take, for example, probably a few hundred pointings to actually map an object, say the size of the moon on the sky. W-FIRST could do it in 2.
Oh, wow. Okay.
And
what are
that
you-
has some interesting applications.
So what applications is that going to get used for?
Well, so you think about when you get a big field of view, what you can do is you can map very large objects, the moon, the Andromeda Galaxy, places that are very large star-forming regions in the sky, and you can do it very efficiently and learn about the whole system as a whole, right? You can learn about it. But also, you can look for very rare events that would be very hard to randomly pick up in a tiny little Hubble image. But if you have this huge moving field, you're constantly taking big pictures, you're going to see interesting, weird phenomena.
So this is equivalent of, after a while, going back into the archive and going, hey, or going on Google Image or Google Street View and looking to see who's picking their nose in their car.
That's exactly what it is.
All right.
So if you catch some stars picking their nose.
Right.
And the equivalent of picking their nose, one example for planets, is what's called microlensing. There's a random chance that a star and planet will pass by a more massive star just in time to get their light bent in just a way that it'll get magnified like crazy and you'll see it here on Earth. And that can detect planets that would be undetectable by any other method.
Really?
And it turns out that W-FIRST field of view is so big that you would actually expect it to find, just by random chance, several thousand planets during its lifetime.
Wow.
Which is comparable to the number that we currently know about, which is about 5,000.
That's crazy. And that's going to be,
And they would be very
directly,
different kinds of planets.
directly imaging them in some cases through that.
Yeah,
the
but very
gravitational-
distortedly directly imaging them.
So looking at it through, a blurry pinhole.
Yeah,
kind of thing.
and you see, unfortunately, it's really kind of sad because they're once and gone. Once they pass, you're never going to see that planet again because it's so faint that without the magnifying effect, you could never detect it.
Would you be able to kind of go back and determine where that planet was?
Yes,
So
so
you'd
we
be
can
able to say-
retroactively figure out what it was doing.
Okay. And then I remember one of the things when we were getting ready to release Beyond Earth, Will Miller was saying he thought that probably the idea of imaging an exoplanet would be something that would be very meaningful to people. Would this conceivably be the kind of place where you would get to?
So this isn't going to take terribly pretty images.
Okay.
So to get a really nice, exquisite picture of an exoplanet, you need a bigger telescope. It's
Right.
just both because you need more sensitivity, but because you need better resolution.
Okay.
Resolution meaning the smallest angle you can resolve, the size
Right.
of your pixels, if you think in some sense,
Yeah.
on your screen, so that you don't want it to look all pixelated, you want to get a good look.
Right.
So you need a huge telescope
Yeah.
to resolve an Earth-sized planet in its habitable zone around a nearby star. And it turns out it's actually because we know where all the nearest stars are, it's very easy to figure out how many of them would be good candidates for this. and for what size dish you need. And it turns out, as you keep stepping it up, you get more and more planets that you can do this with. So with only a 4-meter telescope, which is only 1.5 times Hubble's mirror, there may be 3 or 4 Earths that you would expect to pick up.
Wow.
But if you increase the size of the mirror, that really rises until if you get to a kind of 15, 16 meter, which is about the largest you could possibly launch with current technology, you could pick up 60 Earths.
That's crazy.
And then 60 Earths is enough that maybe you could start to
say
something
we should go there.
Interesting.
We should, that one looks like it has oceans. We should definitely check that out. So once you've got kind of this, so something has magically happened. We're in the future. We are on an Earth at some point in the future where there's a 16-meter space telescope that's finding Earths.
Not even that fantastical.
And in beyond Earth, we've got kind of 2 ways that we've got people leaving. The one kind of canonical one is that everybody goes into hypersleep. You cool the body down, you ship it out. The ship takes a long time to get there. That's pretty straightforward science. I
don't know, but cryogenic sleep is a little tricky, but sure, why not, right? I mean, if you can replicate genomes, you can certainly, do repair damage and things like that. So, I mean, in principle, why couldn't you preserve people long enough to reach some incredibly distant location?
Yeah.
It's a one-way trip, though.
Yeah, no, you're not coming back from that and expecting to be in time for Grandma's
Just because
birthday.
the nearest star is so far away, it's sort of unimaginable. I mean, you think about the fact that the New Horizons mission,
Right.
which is to Pluto, which is going to arrive at Pluto in July, has taken 10 years to get there. Okay.
And that's just to Pluto.
That's just to Pluto. That's just
Right.
at the edge of our own solar system's disk.
Right.
And the distance to the nearest star is something like 50,000 times farther.
So you're going to be...
So even assuming that you get a factor of 100 increase in speed over New Horizons, you're talking 10,000 years to get to the nearest star system, Alpha Centauri.
Yeah. Wow. So that raises the other prospect, which is generational travel. So the idea that, and this is actually the new faction that we announced for Rising Tide, is the Al-Falal. Their whole deal is that they have sent a generational ship, and that's kind of an interesting sociological question. Like, what does it mean when you have people settling on a planet who have never been on a planet before, their parents have never been on it? The only thing they know about planets are that they happened once for people.
Mythological to them, right?
Yeah.
They can look at pictures in textbooks, or they can look at, maybe they have a telescope on board, they can kind of view them, but to actually stand on a surface.
So for 10,000 years, that's a little bit like the last time, that's the
whole
historical
human.
time to Babylon, basically.
Well, that's, in advent of farming.
Whoa.
Agricultural
That's
revolution was 10,000 years ago.
The whole tech tree.
So 10,000, human civilization has been accelerating at an unbelievable pace.
Right.
So we can't even imagine 10,000 years now, because that's the whole of our development from,
I know.
Hunter-gatherer to now.
That's
basically.
before the iPod.
Yeah.
That's crazy.
Yeah, that's
Can't even begin
iPod.
with-
Oh, yeah.
Yeah, that's crazy.
This might be before the BlackBerry.
What? There was nothing before the light. Oh no, there were stone tools.
That's right.
So we've got a question about any news on the search for dark matter. And then we'll jump back into our game real quick.
That's a difficult question. There are 2 ways in which we sort of hope to detect dark matter. The indirect way is dark matter, by the way, is matter like our own, but that emits no apparent light.
Right.
We can only trace it through its gravity effect on other things.
Okay.
And so we noticed the way we detected dark matter is that we have looked at single galaxies and noticed that there's clearly they're way too
Massive.
They're way too massive, in particular in their outer areas compared to the inner. They should be more top-heavy than they actually are, judging by their rotation.
Okay.
And so we know that there's some extra stuff there. The other way is we watch clusters of galaxies interacting, and what we've realized gradually is that there is a cosmic web of dark matter, these sort of spiderweb strands of heavy stuff that's not emitting any light, that just essentially stretch the universe, that all of the visible matter, the galaxies, stars, sit on. And they only represent about 1/6 of all the matter in the universe.
And this is problematic for getting good models of the universe and what it should be doing.
Right,
and, yeah.
right. And so then the question is, what is dark matter? And there were 2 schools of thought on this a few decades ago. One was that it was very dark, just large things like dead stars or things like that. But it turns out that just doesn't work. You can actually basically rule that out as a significant contributor. And so what you're left with is that there must be subatomic particles that we're not
the
picking up.
dust of a dying world.
And so there are
must
searches for those,
listen to the
and there are a
stones
number
of
of
a living
experiments
one.
to look for, essentially, you look for an unexplained impact on something that you've shielded really carefully from all other forms of matter. So it shouldn't be hit by anything. And if it gets a hit, you record it and you see if there's any pattern.
Has there been anything like that? That's reasonably uncontested?
Not with high enough statistical significance.
That you would be willing to say.
So, for example, let's say that dark matter rotated around the galaxy the same way we do.
Right.
Well, within our own little solar system, we sometimes are rotating, since we rotate around the sun,
Right.
sometimes we're rotating with the direction of the galaxy, and sometimes we're rotating a little bit against it.
So we should be getting
So
hit
there should be a
more.
headwind
Yeah.
during certain, and there's some evidence that that's true, but it's very controversial right now. So there are other experiments like that that are just buried deep in caves where nothing hits and look
seeing
for these impacts.
Um,
So I think that in the next few decades we will
You'll
find
get
out.
some good evidence one way
It
or
may
the
be
other.
that it's a decay product of the Higgs boson or something like that. I mean, there could be connections to particles that we know.
Let's Tech Webb, help me out here. I'm kind of half-heartedly playing this game. But is there a tech we should be looking at?
I love genetic mapping.
I like genetic. Oh, gene vaults. I don't think anybody's got gene vault yet. We should definitely get that. Thank you.
Yeah, I love the crazy resources of this game. Floatstone,
Flux-
Firaxite.
Firaxite seems perfectly reasonable to me.
Yeah.
But these are not unreasonable resources you could expect to see on a planet with, some form of life. For example, we've got petroleum right here.
Yep.
If a planet has life on it and it's been there long enough, you'd expect to see some kind of
Which, if it's
hydrocarbon.
macroscopic
Yeah.
and it originated there has to have been.
That's a lot of petroleum. Jeez, that's a 7 yield. Sorry.
In fact, the rise of multicellular organisms on Earth was a very late process, if you think about it. I mean, we spent billions of years with just single cells, and then basically everything else came in the last, half a billion years?
Half a billion, yeah. Now, would you expect to see planets roughly with geological composition like Earth if they're terrestrial? I mean, we were talking earlier about the distribution of things like elements like gold or uranic elements or things like that. So, I mean, is it reasonable to expect to find a planet with big buttery lumps of gold lying on the surface, or?
I don't think it's crazy. I think that the really heavy elements, the elements that are produced in the flash of a supernova,
Yeah.
gold, uranium, things like that, the really heavy stuff, they're kind of everywhere, at least in the stars that we look at, the atmospheres of other stars. And so you could make the assumption that if most stars have this, therefore their planetary systems should too.
Mm-hmm.
It's difficult to prove that with our current data, but I think that's a reasonable assumption. So I think you would expect the really heavy elements to kind of be around.
To be out there.
Now, what might be more interesting is how much of the intermediate stuff that's formed sort of gradually through the lifetime of main sequence stars, up, the things from oxygen, carbon, up to iron.
Right.
Because those are the ideas that stars are born, they produce this stuff and they die, and whether it's by a supernova or a less violent method, they sort of sneeze out their materials all over the area, and then it gets circulated through the galaxy into new gas clouds,
Yeah.
which reform into new generations of stars. And that has definitely profound impacts on the kinds of planetary systems that a star forms. We know this because we've actually looked. We know that stars that are metal-rich, where I mean metal means anything more massive than helium,
Right.
Actually show more planets.
Oh, interesting. Well, which you would kind of expect because there's more stuff for it to kind of accrete around.
It's certainly that mix of heavier metals makes it easier to cool, and cooling is the equivalent of contracting.
Okay.
And that's collapse, right? Because you're always trying to collapse under gravity, but what resists it is the energy that you have to move around. And so if you have efficient ways of cooling, getting rid of that energy, which is through metals, then you can collapse more easily.
And you get a nice compact body that's potentially habitable at some point.
To make how do you make how do you make an Earth versus how do you make a Jupiter or how do you make a Pluto? It's a very different process.
Interesting.
But aspects of the same
Same process overall. I've got this siege worm here that concerns me because I spent last turn alienating aliens.
Yeah, the aliens don't really like you very much when you shoot at them.
I kind of, I'm not going to make excuses for my behavior. I'm going to justify it as species chauvinism.
I would guess they have a little bit of a hive mind, since you shoot one bug and then the worm comes after you.
Well, they
seem to be
do.
working
They do
together.
sort of. The AI kind of handles the aliens as a set, which is.
No, it's
have
great.
words with the
It
designers.
means that they learn from each other.
It's
Shouldn't underestimate the.
No, that's true. It's an interesting question, though. You know, can you get a group of separate species to perform in a way eusocially? If there's
Clearly,
an
there are social organisms.
oh, there's eusocial organisms, but I don't know that we know of a eusocial ecosystem or an ecosystem that functions as more than the sum of its parts. I need to pick something here. I don't know that I need more energy. Production towards wonders might be good. We can kind of squeeze out Gene Vault early on, and I'm not really going to save this game, so I'm going to make.
Yeah, we don't want to record too much of this.
Yeah, exactly. This is nobody's going to be.
It's
terribly
difficult enough to play with backseat riding, I think.
Well, I kind of. This is fun. This is fun. I'll have this guy set up here. Well, let's see. Gosh.
You got to take a shot at them.
Oh no! Oh no! That would be a suboptimal decision.
Yeah.
If it moves up next turn, we'll relocate.
Yeah, judging the aggression of an alien system is.
So actually, you were here a couple weeks ago, and we had a really kind of a cool talk about how you would determine that. And we've been talking about the contact victory in Beyond Earth, and the idea that you would come into contact with a alien species that is benevolent and happy to see you. And then I remember saying, we were like, well, how would you know that they were friendly or not? And you came up with this cool idea of a malignancy index. So if you're observing an alien species that's clearly intelligent, and you're meeting them for the first time, how do you determine whether or not they are dangerous or friendly?
So this is a really difficult question, right? Because you can't talk to them,
Right.
and you don't have any sense of what they consider important or what their art is or anything like that. And so I started thinking. This question took me aback. I started thinking about it in terms of we have scientific instruments. We can measure what the civilization's outputs are.
Right.
And we can count, right?
Right.
Take pictures. So you should have you need two pieces of information: the total amount of energy that the civilization is putting out, and then the total number of citizens in the civilization, because you get an energy per capita. And so I had this thought that maybe there's a correlation between, first of all, if a civilization produces more energy, that generally means that it's higher technology.
Right.
Okay. Or at the very least understands more resources.
Because they kind of, if they're producing more energy, they sort of moved out of the wants phase, and they're into, they have the capability to exercise
They can
more
do
of
it.
their will. Yeah.
And they're doing it. And then the per capita is, how do they divvy up that energy amongst, how much does an individual person being in their civilization consume?
Mm-hmm.
If you think about indexes of the United States versus the third world country, the per capita consumption of resources is much, much higher here.
Right.
And so I thought that a civilization that has both a very high energy output and a very low relative per capita energy output, so one which the individual citizens are conservationists, but the total civilization controls an enormous number of resources, is the least likely to be aggressive or malignant. One that would, because they clearly have what they need and they're not over-consuming.
So they're efficient, and you're assuming because they're efficient, they're rational, and thus not necessarily aggressive.
I'm not saying it's a perfect
Right.
measure, but I think if you were to just take two numbers,
that it would be a reasonable.
because so clearly if they have a low amount of energy and a high per capita consumption, that is very likely to be malignant.
Well, it's a little bit dangerous. It's the whole, we're taking everything and we're turning it into a gun.
Yeah.
Kind of.
Yeah.
Or using it very aggressively. So
Yeah.
then potentially they see you as a resource pool as opposed to, an intelligence that might want to speak with them, kind of thing.
This is in lieu of looking for things like weapons platforms or things you could directly identify. But I like it as just kind of, it's just sort of a sociological model of a malignancy of a completely unknown civilization and species.
So that's a really interesting question for you guys to go home and think about. If you were going to come up with your own index of malignancy, your own way of determining whether or not an incoming alien species was dangerous or not, that it's an interesting thing to think about. It's a very
There have to be
interesting
more
topic.
aspects to it than that, I'm sure.
But without directly observing them at that point. Once you can see their architecture, for example, we were saying,
That's a start.
If you could see the cities that they built, that would tell you something about, if they're, or the number of people that were taking to do it. If they were, for example, using huge labor pools to build giant statues to themselves, you'd look a little bit askance at them.
Yes.
The old Civ.
Do they have a class structure?
Do they have a caste system?
Well, this actually came out of a discussion as to what do advanced alien species look like to astronomers observing other star systems.
Oh, right, yeah.
And we were talking about, I'm sure most people have heard of Dyson spheres, the concept of positioning an array of solar panels or whatever around the star to capture more of its energy, because our sun just completely is wasting most of its energy out into interstellar space, or that's terrible. We should really be grabbing a lot more of it than we do.
Right.
So so if you did that, it would look like a very large, very cool star, quote unquote star. And so we can look for that kind of thing. We haven't seen anything that looks like that yet. But the thing is, no matter what, really, unless you have some physics that we don't understand at all, which I'm not saying that's not a possibility, but let's assume that they, like everything else in existence, radiate waste heat, right? And there's a great study actually being done by a group at Penn State that they looked at just whole galaxies of stars and tried to calculate the maximum amount of waste heat, because it's always coming out in the infrared,
Right.
that they can observe from this galaxy. Now, dust also emits in the infrared, so that can confound it.
Right.
But this basically puts an upper limit on the amount of Dyson spheres that are in that galaxy.
Okay.
And the constraints aren't very strong, but they are scientific. It's very interesting. So they can, I think I've heard things like, maybe no more than 20% of the stars in that galaxy are Dyson spheres. I realize that's not
It's an interesting.
a strong caveat, but there is not an entire galaxy-spanning civilization with Dyson spheres in that galaxy.
That's good to know.
Which is, we couldn't have said that 10 years ago. And the reason we've been able to say that is that we now have infrared-sensitive telescopes like Spitzer and WISE, which was the one that was used for this. That was an all-sky survey.
Wow. And then, for you personally, is there some
I love this stuff.
indicator that you would like to look for? Did you run a side process that
For biosignatures?
For biosignatures?
Yes. I think, let's start with the assumption that they're at least a little bit like us. You can look, even the Earth's atmosphere has changed throughout time as biological organisms have altered it.
Right.
But there are some things you would expect to see if biological organisms were messing with the atmosphere of an extrasolar planet. Just specific signatures of chemistry. And chemistry you can learn from what's a technique called spectroscopy, which is where you split light into different frequencies and count how much energy comes out at each frequency.
Right.
And they leave sort of fingerprint. Each chemical will leave a different fingerprint in that spectrum. And so you can say there's a lot of X or Y. There's a lot more carbon than oxygen. There's a lot more methane in the gas form than there is in the ice form or the solid. And you can learn quite a lot without even being able to take a picture of an object, just from its spectrum.
Wow. And so when you see a lot of methane, for example.
That might be a hint. So if you have anaerobic bacteria. So the other thing is, if you have a planet that originates in a more carbon-rich system, it could be that it would be carbon-dominated. It would be silicon carbide, or it would be ceramic. Most of the planets that we see are from oxygen-dominated systems, where the oxygen locks up the carbon in carbon dioxide. Or carbon monoxide. And basically, so you look at Venus, for example, right?
Right.
It has no plate tectonics. So its carbon has not been subducted into the...
It's all right up there.
Right, it's all up there. And it then went up and created the crazy runaway greenhouse effect that it has now, turning it from what really would be an Earth twin into a horrible blasted hellscape that no one would ever want to go to.
That's a technical term.
Yeah, this was the question I always had when I looked at planets, is that you watch Star Trek and they trip over habitable worlds. Every single system is an M-class planet with aliens on it in a Bronze Age civilization or further, which seems crazy. But the other extreme is you look at our own solar system and it's one terrible place after another. Venus is like acid rain, and 90 bars of pressure, and Mars barely has an atmosphere, and
Mercury is made out of metal and baked
Mercury is
half of the time.
And is tidally locked to the sun. This is another problem.
Oh, yeah.
The same side of Mercury keeps facing. You need a planet that actually rotates.
Yeah. No, I kind of,
And so everything seems to disfavor Earths except for moons.
And that was the interesting thing that Hubble has just identified as well, which is seas on a moon.
Yes. So Hubble did it by a very interesting method. Usually you think about solar system exploration as being done by robotic
Yeah, you
missions
send a
that go out
probe there, and it drops little lure probes, and the probes send probelets, and then...
Which we still do, which we think is great.
Yes.
But Hubble has places to contribute, and Hubble has spotted 6 moons of Pluto, for example. It's going to guide the New Horizons mission as it approaches. But what it's most recently done, which I think is amazing, is by a very interesting method. So the Galileo spacecraft, when it went by Ganymede, which is the 3rd moon out from Jupiter,
Right.
picked up a magnetic field, which makes Ganymede the only moon with a magnetic field.
Right.
Jupiter has a magnetic field. So the magnetic field of Ganymede and Jupiter bump into each other, and they react. That causes auroras, like the northern lights on Earth.
Yeah.
Okay, but these auroras are mostly picked up in the ultraviolet. That means Hubble can see them. So the thing was, the aurora actually rocks back and forth, and it's telling you something about the magnetic field of Jupiter, but it's also telling you about the field of Ganymede, because the experiment was to see how much rocking the auroras did.
Right.
If they did a lot of rocking, then that meant that there was nothing dragging the field lines back. You can almost think of them as like strings in a heavy water that you're trying to pull back and forth.
Okay, but if it's moving just a little bit, it means there's
Then
something
there's
else
resistance.
getting some resistance in
So
there.
what's resistant would have to be a large ocean, a saline ocean.
Really?
And so it turned out that they were not rocking very much. And so instead of it being just an internal dynamo, this was really strong evidence that about 100 miles under the surface is a 100-mile deep ocean.
That's crazy.
Which makes it about an Earth's ocean, or maybe more, I think, in terms of water. Now, very salty water.
Yeah, but still,
so that
water.
we inferred its existence
That's crazy.
under what's just 100 miles of ice.
That's nuts.
And just by looking at the ultraviolet light from Hubble, with Hubble's special instruments that can detect that.
That's crazy. Let's jump back into our game real quick. Got some other cool things here. Geothermal energy. Obviously, if you have an active planetary core, you're going to have some sort of geothermal activity. We got some pretty extreme
A lot of
examples.
circulation.
Yeah, and there's some, again, pretty extreme examples in our own solar system as well, too. Io is basically the poster child of geothermal overactivity. I mean, it's kind of caught right there next to Jupiter, and it's getting stretched and squeezed and pulled apart, and has volcanoes of all sorts of exotic materials.
Jupiter's a real troublemaker. The Jupiter system is a real troublemaker, let's say. We can call it the Jupiter system. You can call it the Pluto system now that it has 6 moons.
I still think it should be a planet, but my vote doesn't
See, I
count.
actually think of it as the Pluto-Charon binary system.
Oh, that's pretty cool. So what are they going to call the other 4 and 5 moons?
Well, they're really small and they tumble in very weird ways.
Oh, that's cool.
Yeah.
So does that mean they're recent moons or recent
No,
like,
that's
captures?
what's amazing. They appear to have been primordial. Like they must have formed around the same time as, oh boy, the worm doesn't like it.
It really, I also lost the worker. But,
Yeah. So yeah, they're old. Pluto has not,
crazy.
they should have been ripped away from Pluto a long time ago.
we're going to purchase an ultrasonic fence real quick. We can't afford an ultrasonic fence. Wow. That's really, I should have been paying better attention. I apologize. So they are not recent captures. They've been there for a long time. Were they just hard to detect because they're so small?
Yes,
Because
they're tiny.
They're
And irregularly shaped, I believe.
That's crazy.
So that's one of the things that's, so anyway, the Pluto system is very interesting. So now we've gone from thinking about it not as a planet to as this very complicated.
As this little planetary system all by itself. It's cool to think of moons potentially as being a place that human beings could go, or planets, being systems. The idea of something like a Jupiter being a place that, has its own structure to it, its planetary structure to it, and being habitable as well too. And aside from, I'm not going to purchase. I'm going to choose production. Aside from Avatar, I don't know of too many other people who've thought about that in that sort of a sense. We're going to build an old Earth relic because I like culture.
Yeah, we're very
messing
cultured.
around here. We are very cultured. I should be building a worker, actually.
We need to build a culture that appreciates this huge space telescope.
Yeah, you notice actually that the worms have calmed down. That it went from orange back down to green.
Oh yeah.
So it's I'm really kind of annoyed about that. I should have. I was all like, oh,
got
let's go off and
satiated.
explore. Maybe he did. He's eating all of these tubers that I was preparing for him. That's all right, who's wandering around needs orders? Oh, this trade convoy is like, I'm not going back there. Don't send me. So what do you
So the
want to do?
upshot is there are a lot of oceans in our solar system now.
That's kind of amazing to think about
More than we
because,
thought.
you know, we, for a while there, I mean, I remember in my own brief forays into, you know, astronomy education, people told me how unique it was that Earth had, you know, liquid oceans and, you know,
No
seas and
village
things like
was
that.
ever ruined by trade.
Oh, let's work together. All right, you can be nice.
We should work together.
Sure, let's do that.
International cooperation.
No village was ever ruined by trade. So, but exotic elements like floatstone. This seems a
智慧和
little bit.
财富
No, go away.
是最
This seems a little bit less likely that you'd come up with some kind of rock or crystal that floats off the ground. But, right?
If
I
it were
mean,
magnetized properly, maybe. If they were able to hang this. Well, certainly if the planet were gaseous, you'd have all sorts of things floating.
including
Of course,
rocks,
you
or
wouldn't
wouldn't
have a
everything?
surface, but
No, but
You could, well, pebbles and things like that.
would
You know,
they?
as long as they get lofted.
So you would have to be blown around the planet for its entire
Yeah,
course of
it's hard to
existence.
picture exactly what this would look like, but I could somehow. Well, you could certainly have a gas giant where there was a dusty disk around it and it was seeding the planet's
Oh, I guess
atmosphere.
so. Yeah.
And this actually this happens. If you look at white dwarf stars, which are dying, dead stars,
Right.
they actually their atmospheres get polluted when the rubble from a planetesimal of rocks falls in. We can actually pick up the signature of planets around dead stars there.
Just from having fallen into whatever's left of
Yeah.
of that.
And it has because the white dwarf's atmosphere is normally so pristine, you really notice when
When
rubble
that
from
happens.
a rocky thing falls in.
So what does that look like in terms of what is that distinctive signature look like? Is that,
Well, white dwarfs are burnt out cores of stars like the sun.
right.
So they're mostly helium and hydrogen. And so if you see silicates or carbon, things like that.
And again,
falling in,
that's a
bits of-
spectroscopic change.
Right. So that's a spectrum again. That's the key point. So for example, when I go and look at young stars that are making planets around themselves in our relatively local neighborhood, we see signatures of certain kinds of rocks. In particular, forsterite, which you would know as peridot, is one of the most common signatures that we see. We see, Jupiter's mass worth or more worth of this forsterite dust and other things like that.
If you're
in
going
different
to
crystallized
rejigger an
structures, we can actually
organism's
tell the difference
genotype,
between
you
the
should
amount of
give it the
magnesium
courtesy
iron
of
in
reading
them.
its manual
And
first.
the reason that's interesting is these form under very specific conditions, kind of like baking them in a kiln,
Right.
raising the temperature to 1,000 degrees and then pulling them out of the fire.
How
Things like
much?
that. So this is a major component of the Earth's mantle, and we're seeing it as a really common dust component around other stars. But the key is these dust pebbles are a micron in size, which is a millionth of a meter. So your fingernail is about 1 millimeter. This is 1,000th the size of that. So these are much smaller than even grains of sand.
Wow.
But many planets worth of them.
Just
Just
Spread around.
rotating around, maybe gathering into larger structures, building up bigger, shattering, colliding.
yeah. Interesting. And that is what
Making
we know
planets.
as peridot.
Yep.
Yep. Very cool. So if you've got peridot on your cufflinks or whatever, it's bits of
Protoplanet.
protoplanet. That's kind of cool. I think that's very neat. Let's pick a tech kind of direction. If you were on a planet and you were settling out, we've gone to genetic mapping. We've decided that we're going to sort of preserve our or keep going in that direction. We could go up in the genetic design field up here. We do need. We've got a little bit of. We could. I don't know that we have any workable petroleum right by us. I should have checked that a little bit more closely. Alien sciences. This has got some potential as well too. There's a little bit of workable xenomass near us.
Xenomass seems the most valuable.
It's
of the resources.
it's a pretty valuable resource to have. We'll go ahead and go in that way. All right. So and of course.
So we still have our worm friend.
No, he's gone. He's wandered off. He's decided to
Why
wreck
does it say
everything.
you can shoot it? Oh, them.
Because the wolf beetles are there. Wolf beetles, are there 2 meter tall beetles running around the universe. I don't know. I understand there's an upper limit on what an exoskeleton will buy you, but I like to think
It's true that the physics doesn't scale with size entirely.
Yeah.
You have to be a little bit different if you're larger.
Yeah. They're still very dangerous. We'll leave them alone for right now. So let's jump back to the studio real quick. Well, thank you very much for coming out to speak with us.
This was great fun.
It was a lot of fun to
I'm honored that you named this crazy telescope after me.
Yeah, it was. We'll put it up on Steam in the workshop if people want a totally balanced, broken.
It's perfectly balanced.
Yeah, totally.
Yeah.
And as long as everybody has access to it, surely it can't go wrong.
Yeah.
Nothing will possibly.
You definitely will not have an entire orbital layer of J greens.
J greens. Yeah, it would certainly give you a lot of incentive to go down supremacy and really go to that orbital domination route. You could have a lot of fun with that. So this Saturday, don't forget Astronomy on Tap at the Auto Bar in Baltimore. Be sure to check that out. Don't forget this last part of Systematic Destiny is up on civilization.com. Thank you guys for tuning in today. Hopefully in a little while we're going to be able to start streaming Rising Tide. We will definitely let you know when we're going to have some of that to show. Next week I'll be back with Stuart. We're going to be continuing our impossible difficulty epic galaxy takeover. We're kind of on that crest. I think the rest of the galaxy just needs to realize that it's under new management and accept that this is the way things are going.
They'll come to your way of thinking.
They always do. It always works out that way. Joel, thank you very much for coming out today.
Thank
really
you for
appreciate
inviting
it.
me.
Hopefully we can have you back sometime.
It would be great fun.
Okay. Thanks for watching. Don't forget to tune in tomorrow. Watch Dave Hinkle play some more Beyond Earth, and we will see you next week.